Midlight total.
Yeah. Cool. I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day again. I just thank you for this class and just this time we have to meet and study your creation. Just help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I'm going to start with a review of linear algebra. I'll try to keep it kind of a brisk pace in here. So I guess the first thing that I would like to talk about is, my notation. I'll keep it real. Oh, rats. I can't quite do that. So take a field, n by n. So what this would be is like not n, m by n. I guess I could use this notation aij such that 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n, and aij is an element of f, right? Of course, for all ij. This would be the set of m by n matrices over f, right? And so here, the field, typically we have in mind either the reals or the complexes, but of course you could use any other field that you want and still reasonably talk about this object. This object is itself a vector space, right? So like definition, if you have A and B matrices, right? And if you have a constant in your field, then we can define A plus B as this, and C times A as this, right? So this defines matrix addition and scalar multiplication component-wise, right? So these, of course, are both for all I and j, which is, of course, is understood to mean I ranging from 1 to m and j ranging from 1 to n. Other important notation that we should know about is column. So we can talk about the like the jth column of A. All right, so what's that? That is A1j, A2j, AMJ. So the jth column is identified as a column vector in Fm, right? Fm is the set of m vectors over F. And of course we can also talk about the ith row of A, which is given by AI1, AI2, AIN. Now that is not an element of Fn. This is an element of F1 by n, right? In my way of thinking, if we definition, right? If A is an element of Fmn, then A transpose is an element of Fn by m, where A transpose ij is equal to AJI for all ij. Okay, so that's how we define the transpose of a matrix. And with that notation introduced, we can say that the ith row of A transpose would be an element of Fn, right? Of course, that's important because when we define matrix multiplication, we end up taking dot products with rows and columns, right? So they have to have the same size and all that. So let's do that. All right, so definition. If A is an element of F, let's say M by N, and B is an element of F N by P, then AB is an element of F M by P, where AB ij is equal to a sum k equals 1 to n of a I k b k j, like that. Now, that is a general definition as long as you understand that the notation has to be taken with the right understanding in the cases that the dimension m or the dimension p drops to 1. Right? If m or p is equal to 1, we don't have an index there. So those are special cases which probably merit separately writing out. Okay, so like, you know, if we have p equals to 1, what's that make b? N by 1, n rows by 1. In other words, this would be the case that b is a column vector, right? Then we usually write b equals to x in that kind of case. And so if you have ax, you're not looking, there is no j, right? There's no j index in this context because there's just one column. Okay, so we just say I, and that's equal to a sum k equals 1 to n of a I k x k, and that's it. And likewise, if we just have m equals to 1, I don't think about this as much, then that would mean, that would give you something like, let's say, yb, well, let's say yb, and I guess we'd just be looking, there'd be no I index in that context, we'd be just looking at the jth index, and that would be the sum, you know, k equals 1 to n of y k b I guess it's kj. Is that right? Actually, I'm worried. Not sure about that, what I just wrote. That's the bad thing about this room is I hear people talking outside and it doesn't help me. It's like a bad kind of quiet. It's quiet enough I can start to try to listen to their voices. I need more noise. Sorry. Just stuck. This would be like a...
Yeah, I think that's...
Yeah, that should be fine. Let me actually do an example. Because I'm worried about it. You know, we could take y equal to, say, 1, 2, and b equal to, let's see here, I need like a 2 by 3, let's say. 0, 1, 2, 3, 4, 5. That would be So here we've got a 1 by 2. This is a 2 by 3. If we calculate YB, how's that go?
6 first.
Does that make sense?
Yep.
Okay, it does. And the result is a row vector, right? See, I am so heavily invested in the world of column vectors. It's hard for me to go over to this wild world of row vectors.
6, 9, 12.
Oh, so you got 6, 9, 12? Yeah. Cool. All right. Okay, so that's the definition of matrix multiplication. Now, of course, you can prove properties of it and all that stuff, and it has nice properties. It's not commutative, but it has many other nice properties. Let's see what I want to tell you about it. Yes. So, ways to look at matrix multiplication. So, and I'll just stick with the context of, not being in the, I'll try to look at the case where A and B are both genuine matrices, all right? So, the one way you can look at this is A times a stack of like column vectors, like here's column 1 of B, How many columns are there in B? N by P, so P columns, right? And so one way you can do this is just, it works out like this. A times column 1 of B, and then A times column 2 of B, A times column P of B. That's a very important way of understanding matrix multiplication. Many proofs flow through this idea. Sometimes I call it the column by column multiplication rule. Now the one we typically teach students, right, is that this is basically what? It's the ith row of A dot product with what? The jth column of B, right? That's how you, and this is that notation, right? You were at square brackets and ij in the middle to indicate matrix. I don't use this notation too much, but it's probably worth taking a second to examine how that formula is this formula. All right, let's think about that for just a second. Why is star the definition? So why is star equivalent to my definition of matrix multiplication? Well, if we look at AB, the ijth component of it, as the sum k equals 1 to n of a, I, k, b, k, j, we just need to think about what's the definition of, what is this, aik? Well, this is the kth column. It's k equals 1 to n. This is row I of A, and this is what? This is row, not row I, my bad. That was actually row, that's not even row A. I'm still wrong. I'm a dummy. What is this? This isn't row, it's not a row of A.
That's row I.
This is not row,
Sorry,
row K, right? Row K of A, right? Is row K of A because the I is fixed, right? I is fixed. So it's row K of A, and this over here is column K of B, I believe. I did that wrong. I'm sorry. This is going to happen a lot this semester.
That's row I. Yeah.
That's row I. That's
Column J.
column J. All right, thank you. And that's still not quite right, because really, it's not just that, right? It's what? It's the, to be more pedantic, it's the kth component, right, of column A, and it's the kth component of column B, and that is, by definition, the dot product. So dot product's a funny thing, right? Like, you can define dot products of row vectors and column vectors if you're willing to take dot products of dissimilar objects. And it is not unusual as you're reading like linear algebra texts or like literature, see people do this. Like, it's like just annoying. I mean, technically speaking, from a purist perspective, I want to take dot products of column vectors with column vectors and row vectors with row vectors, right? But it's convenient to have a notion of taking a dot product of a column vector with a row vector for this purpose. And it also makes sense, right? I mean, really we're just talking about thinking of both of them as vectors, n-dimensional vectors, and taking the dot product. And so there's that, yeah. There's also a, like, if there's a column by column rule, there's also a row by row rule. So there's something like that you can also write down, all right? But instead of looking at the chopping up of B into columns, I think you look at the chopping up of A into rows, if I remember right. So if we have like, you can also look at AB as like row 1 of A, row 2 of A, right? All the way on down to the what? How many rows are there in A? M as in mummy. That times B, and that's going to be what? It's going to be row 1 of A times B, row 2 of A times B, row M of A times B, right? I mean, that's got to be what the rule is. Now, actually, if you know one of these rules, you can derive the other if you study properties of the transpose, because transposition can convert matrix column products to row matrix products. So transposition is worth talking about for a minute. So let us do such. So just so you know where we're going, I'm just spending the first little story arc of the course setting notation for matrix examples. By and large, we're going to take f equal to the real numbers. But this is an important example, so it's important for us to know what the notation means. So we're getting it out of our system. Now, so what's the transpose? Oh, I already defined the transpose. I did do that. Yep. So theorem. And this is pretty much on every one of my first tests in college. College algebra. What's wrong with me? Linear algebra. So if we have A is an element of, let's say, f m by n, and B is an element of f n by p, then A, B transpose is equal to B transpose A transpose. There's a right way and a wrong way to prove this. The right way to prove this is using index notation. The wrong way is any other way. So here's how it goes. We have A, B, transpose. We want to look at, say, the ijth component of that. All right? Well, that is equal to, by definition, AB, JI, right? Really do need, I mean, some people would say you don't need the parentheses. I personally need the parentheses. I need the parentheses to believe the student knows what they're doing, personally. But anyway, here it is. So that's, by definition, the sum over K equals 1 to, let's see, A times B is defined as K equals 1 to N, right? Of A, in this case, JK, B, KI. You know, putting the I first and the J second is not written in stone. Obviously, you know this. Those are just letters. Okay, so then you go, wait a minute, that is exactly the sum k equals 1 to n of, well, it's B transpose ik, and that's A transpose kj, where I've taken the liberty of exchanging the order of the product, and that makes sense as long as we're over a field which is commutative. In fact, everything I've said so far is equally true over a commutative ring with identity. That'd be a nice course to teach, is like matrices over a commutative ring. There's many things I'd like to learn there that I don't know. But anyway, eigenvectors are way, way more nuanced in that context. But anyway, so this is exactly the product of the transposes in the opposite order and the ijth component. But since this holds for all ij, therefore, you know, AB transpose is B transpose A transpose. This is the so-called sock shoes formula, right? Any questions? No. Okay. So if you use that and you were to take the transpose of, like, you know, that equation we were looking at over here, like when you take transpose, it switches columns to rows and rows to columns, and so you'd be able to get from the one rule to the other with that. Okay, enough about that. Let's go on. So the other important, oh man, look at that, junk. Did that go in? No. It felt like it did, but it was short. It was an air marker. Let's see here. So definition, trace of A is equal to the sum I equals 1 to n of A I for A an element of Fn by n. So that's to say it's a square matrix. So trace is an important, very important operation in linear algebra. It's something we can calculate for a matrix that reveals something about the matrix. You might remember the trace is the sum of the eigenvalues, for example. And the trace of similar matrices is equal, right? What's a similar matrix? We'll get back to this more, but A and B and Fn by n are similar if and only if there exists, let's say, P in GL and F such that B is equal to P inverse AP, where GLN F is equal to set of invertible matrices, invertible n by n square matrices, right? So how would you define GLNF? I mean, you could define it to be, we could define that separately, right? GLNF is A in Fn by n such that the determinant of A is not equal to 0, right? That serves to define the set of invertible matrices. All right, so, you know, properties of the trace. The trace of A plus B is trace of A plus trace of B. The trace of C times A is C times the trace of A. And more interestingly, the trace of AB is equal to the trace of BA. And that's not just for square matrices. This one, as long as, how can I say this? Like you have to have A an element of, let's say, F n by P, and B an element of F, oh my bad, AB, P by N, right? So this is actually a very interesting formula because it's saying that the trace, this is like, this looks really simple, and it's less impressive when you think about it in terms of square matrices. But if you take a step back here, we're comparing A times B, which is a, A times B is a n by n, and B times A is a what? Well, it would be a P by P, and somehow this formula for the trace has these being equal. That's really kind of surprising. I'm going to go back to here. Actually, I'll go over here. Let's,
What does GL stand for?
general linear group. So G, L, and F, general linear group. Little GL and F equals just F n by n, but thought of as a the general linear, well, yeah, fine, linear algebra. And so I could say more, like you could think of it as an associative algebra with respect to matrix multiplication. If you want, you can think of it as a Lie algebra with respect to the commutator bracket, but I think I'm getting off track if I start talking about that stuff. I just, it's common vernacular general linear group, or you could say set of invertible, set of non-singular matrices, right? But the proof of this trace identity is simple in index notation, right? So like, here it is. Trace of AB, sum over, let's say, I of AB parentheses II, right? But that means the sum over I, sum over K. And so here the I ranged from what? 1 to n. The K ranges from 1 to P. And here we've got AIK, BKI. And so it's very stupid. I mean, like basically, you have to prove that the order of finite sums can be exchanged. Now, if you're like me as an undergraduate, you don't believe it. You're like, what do you mean you can exchange the order of finite sum? Who says so? Well, no one cares except for me, right? Precious few people actually care about that, but that can be proved by induction. If you make an inductive definition of the finite sum, you can prove the order of sums exchanged. But actually the exchanging of sums like that is actually using the distributive property. It's actually kind of interesting if you write it out for like, I don't know, P equals to 3 and K and N equals to 2 or something. You'll see it's an interesting use of the distributive property. But so this is just commutativity of the elements, and then of course I flip the finite sums, and then you look at it and you go, oh, but that's the sum over K equals 1 to P of BA, the KK component of it, right? Which of course is the trace of BA. And there you go, we've proved that the trace is symmetric in this sense. Of course, another interesting property of the trace is that the trace of the identity matrix, the n by n identity matrix, is equal to n, right? So the trace of the n by n identity matrix is equal to n. So trace actually connects us with trace of the matrix connects us, the trace of the identity matrix connects us with the dimension of the underlying vector space. That's why one of the popular proofs proving the invariance of dimension for a vector space hinges on this trace identity, actually. There's two ways that I know of. I'm sure there are probably dozens, if not hundreds, of ways of proving the dimension theory in linear algebra. But one way to prove, like the essential theorem is that if you have a vector space and you have a spanning set, which is also linearly independent, right? And if that spanning set has finitely many things, then of course we call that a basis. And if you have any other basis for that vector space, it must have what? The same number of elements. We call that number of elements the dimension. So the one proof of that theorem basically rests on using the trace and converting one basis to the other and looking at the matrix of the transformation from the one base to the other. Because the argument's symmetric, you can get basically the trace of the change of coordinate matrices from one base to the other one way, and the other way, they both, well, the product of the change of coordinates one way and the other way is the identity matrix because they're inverse. So you get the identity matrix with respect to the one dimension from the one product, and you get the identity matrix with respect to the other dimension with respect to the other product, but the trace of the matrices are equal, so you get then the trace of the identity matrix are equal, but the one identity matrix corresponds to the number of elements in your first basis, and the other identity matrix corresponds to the number of elements in your second basis, and so then they're equal. And that proves that the dimension is of a vector space is well defined. The other proof of this rests on these plus-minus theorems, which are built up from induction, that if you have a linearly independent set and you take away a vector from it, it's still linearly independent, right? Or if you have a spanning set, right, and you adjoin to that something that's in the span of those vectors, well, that's necessarily linearly dependent. Let's see here. On the other hand, if you adjoin to the spanning set, something that is outside of the span, right, then the enlarged generating set will still be linearly independent if it was before. Not really saying much if you really just think about it at sort of like a surface level thing. You're saying that if you take something that's not a linear combination of the other vectors, then it's not a linear combination of the other vectors when you put it there altogether, right? So like if there's no linear combinations before, there's still no linear combinations if you add something that's not in a linear combination. Like if you start saying it in these kind of words, it almost seems like you're not saying much, but you're actually, to prove these things, it takes a while to do it carefully. And I'm not going to do that in here. All right, because we know these things already. All right, so, yeah.
So here, in the trace of the identity equals 7, since we're using an arbitrary field, then that mean the identity of the field added n times?
Yes, so here I mean n times 1, where 1 is, an element of the field, which is the multiplicative identity. That is true. And I am working, admittedly, I work characteristic 0. You're right. So if we're in, yeah, what if you're working in like characteristic 3 and you've got like a 6 by 6 matrix? How's that all sort out? Like, I don't know. There are issues there that I have not faced. Some of them are uninteresting, I suspect, but
Characteristic 0 basically means the field is infinite.
Yeah, the characteristic 0 means that no matter how many times you add 1 to itself, you never get back to 0. In contrast, if we work over the field like z mod 2, right, 1 plus 1 is 0. So that's, the characteristic of z2 is 2. That's a characteristic 2 field. That's kind of the worst. Any prime, z mod any prime is a field. of characteristic P. And those are finite fields. However, you can look at the rational functions over the field of characteristic P, and that will be an infinite dimensional field of characteristic P. So just because you have a finite characteristic doesn't mean it's a finite field. There's infinite fields with finite characteristic. There's a whole wild world of field theory out there to learn. But anyway. All right, so good. Now let's go on. Uh-oh. Well, if I was off camera, my apologies to the... Oh man, I might have missed the things I just wrote over in purple over here. Oh well. It's okay. Yeah, I didn't write... all I wrote there was just GLN again, so I don't think you missed much. All right, let's go on. So, definition. EI is an element of Fn, which of course is Fn by one column, right? Where EI, the jth component, is Kronecker delta ij, which is 1 if I equals to j, it's 0 if I is not equal to j. Someone wants to create a group chat for Calc 3. I will allow it. Yes, tomorrow. Actually, that would be one. I love group chats for my courses. If I could be part of them, it would be more fun. But let's see here. So this is the Kronecker delta, right? I think I've talked to you about that before. But yeah? I think so. All right, so you know, here's another application of it. If you look at the n by n identity matrix, you look at the ijth component of it, it is Kronecker delta ij. So like it's the components of the identity matrix, among other things. So this, of course, is the standard basis for Fn. And we also talk about Eij. And if we look at the kth component of that, all right, then this is going to be Kronecker delta Ik, Kronecker delta JL. These are the so-called matrix units. Although that's unfortunate language in some regard because they're not invertible matrices. They're just matrices that have all zeros except for 1, right? These are rank 1 matrices. They're certainly not full rank. They're certainly not invertible. They could be square. They could be rectangular. I think in the case that they're square, I can write the most interesting formulas. So let me just, for the sake of just trying to, you know, I woke up I didn't get enough sleep last night, so I'm going to keep it square, okay? So here, this isn't square. This Eij would be an element of F, let's say m by n, all right? Oh, fine. We'll be okay. So, all right. So let me work it out here. So here's the thing. Eij, the kth component of it. All right. So it's equal to Kronecker delta Ik, Kronecker delta JL. All right, so let's see here. I'm trying to think. I can't do this stuff in my head. I gotta write it out. So I is 1 less than or equal to I less than or equal to m, right? In fact, I and k are both like that, right? So this is sort of an m by m thing, right? And on the other hand, the j index is inextricably linked with the L index. Here we have 1. So I should have said I comma k here, right? Fine. One less than or equal to j comma L n, right? So this is a n comma n thing, right?
But isn't the delta just a number?
It is just a number. But yes, good point. Technically is not equal to that. Okay. Let me put some quotes here because I'm being fuzzy, admittedly. But what I'm trying to say is that I can build this as actually a I mean I can
that makes sense when you span over the item. Okay.
Yeah, let me all right, so I think I can do, oh, good grief. EI transpose, or no, EI, I mean, there's two choices, all right? I'm either going to be right or wrong. So I think it's this. I'm sorry. This is not helping. I'm not writing anything wrong here. I'm just not getting to the point, and I'm making it more confusing than it needs to be. You got to know when to burn some bridges. So let's do that. All right. So what I was trying to get at, let me be less obtuse here and do is example 3, example 2. I don't know. How about this? If I want to build, let's say, E13, there, and I'll try to do it as a rectangular matrix, which is really ill-advised. I told myself 5 minutes ago to stick with square matrices. If I could take my own advice, we'd probably be better off. But oh well, let's forge ahead. All right. So, what is this? What is this? I mean, this is. I think we can look at this as 0, 0, 1. No, other way around. My bad. Maybe we can. I'm sorry. I'm trying to think of this as this is a 2 by 3 matrix. I want to write it as like a 2 by 1 times a 1 by 3. Okay, so the 2 by 1 that I want is just the row vector 1, 0, I think. And the 1 by 3 I want.
0, 0, 1.
Oh, I'm sorry. I'm a dummy. Is this a column vector or a row vector? Grief.
That's a
column vector. So 1, 0. This is a 3-component row vector. All right, so, and there's a silly example of the row stacking identity I was talking about. So there's that. Now, let me introduce some. So let's think of it this way. This is E1 times E3 3, and I'm going to put a bar on it, transpose, because it's a different, it's not the same dimension, you know? So like this is part of a larger thing that I always have to look at my notes. If I was looking at my notes, then we would probably have wasted less time here, but oh well. So if I do Eij, I can build it as like Ei, Ej, bar transpose, where Ei is an element of, you know, F, M, and Ej bar is an element of F, N. Right, so then this is a what? This is a M by 1 times a 1 by n, which is an m by n. That makes sense, right? The dimensionality here. My point to you is you can build the matrix units from the standard basis multiplied, which is, and you can check this, right? You can check on this that this actually is consistent with that definition, right? So in the case that for square matrix, you can just write Eij is what? Just Ei, Ej transpose, and you can just, you know, use the standard basis twice, right? I mean, like that, yeah. Now, the reason I'm telling you about all this is it's super nice to know about this when you're faced with problems that are of an abstract nature and you're trying to calculate things across the basis of the matrix units. For example, fundamental lemma. And I'm going to derive it for us as we do it. How about this? If I have Eij times EKL, and I'm saying these are both square, it's still in the square case, all right? I'm pretty sure this lemma has an extension to the case that they're rectangular, but they're still multipliable. There's some other fancy word. When can you multiply two matrices? What do you call that? I say that they're multipliable, but there's some other word like starts with a C. I've forgotten it. It doesn't anyway. I'm not a matrix theorist, so whatever. But all right, so you just write it out like Ei, Ej transpose matrix multiplication's associative, so it doesn't matter. Which we don't need parentheses or anything here, right? Because it's associative. And then like there's a fundamental lemma about the standard, the fundamental theorem, you know, remark I should have probably made is if we have Ei dotted with Ej, right? That is Ei transpose times Ej, right? And that is the Kronecker delta Ij. So in other words, the standard basis is orthonormal. Its dot products are either 0 or 1, which if we understand the definition of vector length as usual, that means the standard basis all has length 1, you know. All right, so with that lemma in mind, you see how this simplifies? See, this just gives us Ei. This gives me Kronecker delta Jk El transpose, and then I can move the scalar out. My bad. Kronecker delta Jk, right? And that is Kronecker delta Il. And I'll put the Kronecker delta Jk last just to make it look like, well, I mean, however you want to write it, but, oh, my bad. I don't get to do that, do I? Don't listen to me. That's nonsense. Look at that. That's just that'd be really disconcerting. If that happened, that would be a shame because that would mean I got a number equal to a matrix, which would be a really bad place unless we're in one dimension. That's not the case, right? That's not the Kronecker delta. That is the matrix unit. So what we actually have here is Kronecker delta Jk E Il. Yeah, so that's the fundamental lemma. E, Ij, EKL equal to Kronecker delta Jk EIL. You can solve tons of problems with this identity. All right, so there's that. So what did you spend the lion's share of your time talking about in linear algebra? What did you talk about mostly in linear algebra, at least to start with for quite a while? You talk about how to solve systems of equations, right? So let's just review that, you know. Let's review that. But I'm going to review it from like 20,000 feet, all right? I'm gonna take a really bird's eye view of the topic, and I'm going to tell you about something that you may or may not have actually seen in linear algebra that actually is the most important thing that you were never taught. I know this from my own personal experience because it wasn't really emphasized in my undergraduate linear algebra course either, and it in some sense crippled me for linear graduate level. Before we get there though, a system of m linear equations in n unknowns. So how's that look? Something like a11 x1 plus da 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 plus a1m n rather xn, and this goes on, right? am1 x1 plus da 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 plus amn xn equals, so I usually write a b over here, b1 over here, bm da 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 da. Here you've got m equations, right? So if any of these, then it's non-homogeneous, right? Okay, so what do? We learned that we can solve this by by substitution, right? But then we get tired of writing variables, so we introduce the augmented matrix notation, right? So basically you say, oh, well, I can look at the reduced row echelon form of the matrix A with B concatenated over here, and you know, this is particularly nice, right? And stuff over here. Anyway, basically we can read off the answer, right? From that. If we just, this is the Gauss-Jordan elimination method. Now, of course, before we get to there, I really should have mentioned, like, what's the in-between part of this I should mention, of course, is we can look at this in terms of matrix multiplication, right? This is equivalent to saying, well, matrix A times vector x equals to b, right? We can trade this set of equations for one matrix equation. That's also very nice. If A inverse exists, then x is equal to A inverse b. Hooray! So we can solve it in one matrix multiplication, solve the whole system. But what's the rub, of course, is that the inverse matrix doesn't usually exist. And even when it does, it's more computationally intensive to calculate the inverse to the system than it is to just solve the stupid thing, right? And that makes sense because, of course, finding the inverse entitles you to the solution of every single possible system, no matter what the b is, right? It's a recipe for how to solve any matrix with this particular set of equations. All right. But the other thing we talked about in linear algebra is that basically you start out with A with B like that, right? And then you do a row operation, and then you get to like row 2, da da da. Eventually, you get to the reduced row echelon form of A with B, right? And so there's like row operations, either additions, swaps, or scalar multiplications, right? And the thing is, in each case, the ith one is equal to some elementary matrix E, right, times the the one right before it, right? I guess k might be the number of row operations if I did my numbering right. Row 1, row 2, yeah, I think so. So if it takes k row operations, it takes you k elementary matrix multiplications to get from the starting thing to the ending thing, right? But basically what that means is that specifically that you can write this is equal to like the kth one, the k minus 1th one, all the way down to this, right? And so this is the reduced row echelon form. And of course, the other thing you prove, hopefully, is that the product of elementary matrices is also, again, an elementary matrix, right? In fact, if you do k-fold row operations, it's equivalent to one single sweeping row operation. You can look at it that way. Now, so check this out. We have the formula RREF of AB is equal to E times AB. But what did the matrix, the column by column matrix rule say? It said that this is equal to EA, EB, right? Right? Okay, fine. So check this out. Theorem. If the sum over Ci column I of A, I equals 1 to n, equals to 0, then the sum I equals 1 to n of Ci column I of EA is equal to 0. And in fact, this is actually not just an if-then. This is actually, to be more honest, this is a if and only if. So how do you get from here to here? You just multiply by E. And use the fact that, you know, E times column I of A is equal to column I of EA. What is this thing I'm proving for you right now is known as the linear correspondence. So what it says is it says that any linear combination found in the reduced row echelon form of the matrix must also be seen in the original matrix itself. This is really, really nice. Example 3.
You said it's called linear correspondence.
Yeah, the linear correspondence. Or as I call it, the CCP, the column correspondence property. So when we start up again, I will use the projector to show you some examples of this in action for some specific and ugly matrices. So.